Okay, so the final talk of this session before the discussion, Yimeng Tang going to tell us about a dark matter deficient galaxy.
Can you hear me? Thank you. Hi everyone, I'm Yimeng from UC Cruz. I'm just a graduate student here. So it's just great to be the last one today. So I hope you are still awake to hear my talk. Unfortunately, I have to show this talk again. I mean, it's just so classic. But different from the other two talks, I want to emphasize, and although there's like some disagreement with the model prediction for the dwarf galaxy, the dihedral mass, that usually people believe that dwarf galaxies should have a larger fraction of dark matter compared to the mass ones. But recent years, people have found a lot of just two dark matter deficient galaxies as the exception for that halo mass stellar mass relation. So DF2 and DF4 in GC Pimp2 group. So they are two ultra diffuse galaxies, and they have large mass, similar mass for those two galaxies, kiloparsec, and the dwarf galaxy mass about 10 to the 8 solar mass. And how can we know they are dark matter deficient? So we use CAD spectrum to measure the velocity dispersion. You can see the velocity dispersion is so low, like only 5 to 10 kilometers per second. And this is agree with the no dark matter model. It's this shade, and it's just way smaller than the normal dark matter halo. But DF2 and DF4 is not just interesting because they have dark matter deficiency, but they also have unusual group clusters. So the group clusters of DF2 and DF4, they have a very small color spread. You can see the white test here compared to normal galaxies. And also, those group clusters, their colors are so close to diffuse starlight. I would not say this is super weird for those galaxies, but once you see the group clusters are also overluminous, you can see the group cluster luminosity function. They're top heavy, about 1.5 magnitudes brighter than expected, and also large in size, like 6, 7 parsecs, so it's just pretty large. So the group cluster luminosity function is very interesting thing to explore, because usually galaxies have a Gaussian like GCLF. I showed 3 examples here. They have different mass and different group cluster numbers, but they all follow almost the same shape. So if you just consider the DF2 and DF4, just so weird, and that's the only 2 cases almost we know so far for those galaxies have such like top heavy. I mean, the peak magnitude is huge. Not only it's brighter. So a natural question is, DF2 and DF4, they are dark matter deficient, and they also have top heavy group cluster luminosity functions. Is there a connection between those two? We don't know the answer, but the opposite way to see this problem is, can we find other galaxies with top heavy GCLF and see if they have, if they lack dark matter? So we're just very fortunate to find another one, FCC224. So I just showed the HST image here. It looks like so similar to DF2 and DF4. It is also a ultra diffuse galaxy, although it's in 4-nest cluster, not in galaxy group. And if you see the group clusters, like those ones, they're so bright and the colors are just similar to each other. And FCC224 also has a similar mass and the size compared to those 2 galaxies. So they're just so similar to each other. But publicly available data for FCC224 is not good enough, so we request the new HST observation. So we can further explore this galaxy. Let me just show the results. So the first part is the group cluster colors. So here I show a color magnitude relation for group clusters. So here is the group clusters we have identified. So if you just see the color on x-axis, the species have almost the same color. And also it's only a little bit bluer than the starlight. So those properties are just so similar to DF2 to plot FCC224 here on the plot. And from the color information, we can conclude that FCC224 just have a single burst star formation history. And this is also confirmed by our SC fitting going with the spectroscopy. And the SC fitting find a stellar age very old, 10 year, and metal pool about minus 1.25. And we don't see color gradient of the starlight, so it's another evidence of single burst star formation history. And also we confirm these galaxies also have a top-heavy luminosity function. So I show the normal distribution you expect, and the red histogram is FCC-54. So you are missing a lot of objects here, and it's just very similar to DF2 and DF4, but it's not as extreme as DF2 and DF4. It's only like about 1 max brighter than expected, but it's already very unusual. And when we go to the globular size, we can resolve these galaxies just very nearby. And we see a diversity of globular size between DF2, DF4, and FCC-54. If you see the plot here, x-axis is the GC size. The DF2 and DF4, they are larger than the normal dwarf galaxies. The FCC-54 is smaller, and it's just as big as the Milky Way clusters. But I mean, for the Milky Way clusters, they are small because you are in a very strong tidal field. You are a massive galaxy. But how can FCC-54, a dwarf galaxy, and even an ultra diffuse one, have such a small globular size? So one way to think about that, maybe you have a high-speed dark matter halo, where you are just to measure reach, and you have the tidal field very, very strong. And here just showing like if you can, the GC actually has some dependence on the other properties of the galaxy, like galaxy luminosity, like the color, and we just remove that dependency. And if you do that, the contrast is even extreme. The FCC-54, just the size is about 35% than you expect. And also considering you have seen the overluminous of the GCs, so they're also very compact. So it's just hard to explain here. So we have other ideas, and we have other results. So also different from DF2 and DF4, FCC-54 GCs show a mass segregation with brighter clusters closer to the center, and you have center ones in the outer part. So this is not exact for normal dwarf galaxies. And if you see the image, you don't have a nuclear star cluster. So there is another case people have been studying the NGC 5846 UDG1 also have a mass segregation. And people explain that with like more orbital decay of the massive GCs, we have massive GCs here. And this is due to the dynamic friction. And also if you have a cold halo, they can never just go to the center. You have a cold solar, you never have a nuclear star cluster. But as this model fit FCC-54, we need direct measurement of the dark matter content of this galaxy. So we have some preliminary results. We just use the newly take spectroscopy to measure the velocity dispersion of this region within 1 RE, and we have several clusters there. And we find they do have a lower, very low velocity dispersion, both from the GCs and the stars, consistent with no dark matter model, and very it's very low value compared to the normal. A warning is currently we only have data with the 1 RE, and we are just trying to take the other GCs on our squared, and hopefully we'll get that result. So here is a summary of the similarities and difference between those 3 galaxies. We see those 3 galaxies, they are all present UDG. They have homogeneous clusters in each galaxy, and they have top-heavy GCLF, dark matter division, although the FCC-54 has a preliminary result. And they also show some difference, like cluster size and mass segregation and the environment. So just go back to the similarities. The natural question is, although I mean we only have 3 galaxies here, but you can ask the question, what's the relation between those properties, especially the top-heavy G7F and documentary deficiency? And the thing is, because the top-heavy G7F just has a close physical connection to documentary deficiency things, we almost only know the 3 galaxies with top-heavy G7F, and these 3 galaxies are documentary deficient. And so we need a big sample. Once you know if the top-heavy G7 is really a good indicator of documentary deficiency, you'll easily find a really big sample in like new generation surveys, like maybe they are documentary deficient galaxy candidates. And go to the theory part. We can get a lot of information from the observations. I want to like one step at a time to explain each observable here. To get top-heavy luminous function, usually there's 2 ways to make it top-heavy. One way is if you have just higher initial mass for each globe cluster. So for both galaxies, you can say, okay, you have galaxy merger and the collision to create like a dense gas environment. Will have like very high star formation efficiency, or you have a strong tidal field to disrupt the medium mass species, so you only have the high mass species. And maybe you also have other mechanisms. And you have some other things, like you have to see like you are ultra-diffuse galaxy. Your mechanism has to fit your ultra-diffuse galaxy. And also you have your GC and galaxy color tell you you are OML4 single burst system. And the GC size tell you have to have a strong tidal field, or maybe there's other missing mechanism we don't know. And mass separation predict the other way, compared to the what you can get from the GC size. So yeah, maybe there's also some missing information we don't know. And the preliminary results tells us it could be documentary division or at least a core halo. So I think what we need to do is just to put your favorite mechanism from each box I'm showing here, and you just put them all together as pieces of puzzle. But you can see there's something like disagree with each other. Like you predict core halo, you predict copy halo, you predict documentary division, you predict primary ridge. So far we don't have a really good explanation for these galaxies. So we really need help from the series in this fall. So yeah, just leave the summary here. I'll take questions. Thank you.
Thanks.
Hi, Jay Baptista from Stanford. Very good talk. I'm really interested in thinking about the tidal disruption GCs and galaxies, and although DF2 and DF4 globular clusters might be more larger than the FCC globular clusters, do you think it could have been at some point that the FCC 224 globular clusters could have had some, or at least the galaxies had some sort of non-negligible baryonic component, such as like a gaseous disk that might have been stripped due to some interactions in the group? Like that could also provide some sort of tidal shocking, which could have made the GCs much smaller than you would expect them to be, at least compared to DF2 and DF4.
Yeah, that's a good point, but it really depends on when you have that interaction. There's some theory work predict that the GC size finally it has nothing to do with the initial condition. Like if you have a much compact GC at the very beginning, it always expand later. But once you have very recent, I don't know the typical time scale, but I mean you have to know like these galaxies are old Quadrant 1, so there could be some concern on the interaction time. I'm not quite sure, but that's a possibility also.
Thank you.
More questions? David.
David Koo, Santa Cruz. I wanted to know what are the reasons that one could exclude a bullet cluster type of event where you have two objects plowing into each other, dark matter separates. What are the arguments against it, I guess is what I'm asking, because it gives you the shocks that you might need, gives you different IMFs, and et cetera, et cetera.
Yeah. I didn't exclude that. I just put it here. You have the facility to have the collision, but I think the question is, can you find a partner of this galaxy because you have two galaxies together? Maybe you have produced some other galaxy at the same time, and you need to find them, right?
That was what Nir was going to ask too.
Yeah, sure.
Okay, well, let's thank Yimeng again, and that will conclude this afternoon session.